Now, let's move on into the next section, where we look at processes such as crushing, drying, and mixing. So in this slide, we can see a series of different machines used to reduce material size. So breakage is a topic often found in research and development, and that's due to the complexity of breakage physics. So here is an example of a cone crusher, and as the rocks fall from the top, they are pressed by the rotating cone against the inner walls and broken into smaller pieces. So Eden will allow to simulate such a complex machine and provide fundamental insight to understand the breakage process in this machinery. So for example, the compressive forces and power requirements can be measured. It's also possible to see areas of the cone geometry where compression happens and how the inlet affects the fit of particles into the crusher. This slide shows some data analysis of the same machinery, and the image shows a crushing process where particles were colored by normal force. You can see the graph on the right shows the mass flow through the cone crusher, and we can see that decrease with eccentric speed. That is the rotation speed of the cone. It makes sense because the faster the cone spins, the less time the rocks will fall before being hit again by the cone. In this video, we show the inside of a mill. And as we all know, it's a key machine for grinding materials in mining. And the potential analysis for these machines could include, for instance, mixing effectiveness. So we can determine the minimum time required to achieve a certain mixing quality. Also to understand the mixing process, so you can study particle trajectory, and this can be analyzed visually. Also wear. Since breakage occurs due to collision against the mill walls, high levels of wear will be observed and estimated, and that is a very important area. Also, we can study the effect of field levels because it will dictate the grinding effectiveness and time. So it's interesting to visually analyze the material flow behavior. And that's why coloring particles and geometries according to their properties, for example, forces or velocities, is very useful to understand the process. For example, this image at the bottom right shows different areas of flow. So we have the flowing area, where most of the material flows around and is slowly grinding itself due to friction. We also have the takeoff area at the top, the freefall area, where the material and the steel balls accelerate under gravity. And we have the impact area, where the most aggressive milling takes place as a result of the impact. So the video at the bottom, the particles are colored by velocity, and it shows how the mass of material change from the rest to the steady state. So due to the initial state of rest of the material, there will be a peak in power to start with that is required to move the mill, as the graph at the top shows. However, as the mill gets into a steady state, so does the power. Dynamic wear analysis is also useful, as I mentioned before, and the video at the bottom right shows the wear of the inner surface of the mill from loading onwards. So this allows to identify areas of greater wear and propose measures for preventing failure of the equipment. Our next example here is a roller crusher. So in terms of analysis, roller crushers are similar to cone crushers. So common study parameters include the size reduction ratio, wear on rollers, but also compressive forces on particles, and as well as the reaction forces on the rollers.